Imagine an agent learning to navigate a complex environment, not from explicit instructions but through raw trial and error. This is the essence of reinforcement learning, a paradigm distinct from supervised or unsupervised methods. At its core, an agent interacts with an environment, taking actions, observing new states, and receiving scalar rewards or penalties. The goal is simple: maximize cumulative reward over time, but how does it learn what action to take, in which state, to achieve this? Enter deep Q networks or DQNs, a pivotal advancement that merges Q learning with deep neural networks, instead of a traditional Q table, which becomes intractable in high-dimensional state spaces. A neural network approximates the Q function. This network, typically a convolutional neural network for visual inputs, takes the current state as input and outputs Q values for all possible actions. A higher Q value signifies a more desirable action in that state, leading to greater future rewards. Training involves experience replay, storing past state action reward next state transitions in a replay buffer. The network is then trained on minibatches sampled randomly from this buffer, breaking correlations in sequential observations and stabilizing learning. Another critical technique is using a separate target network, a delayed copy of the main Q network. This target network computes the Q values for the next state, providing a stable target for the Q value updates, again enhancing stability and preventing divergence. Consider autonomous drones performing complex aerial maneuvers, or sophisticated trading bots optimizing portfolio allocation in volatile markets. DQNs enable these systems to adapt and learn optimal strategies without human intervention. Unlike supervised learning, which requires vast labeled datasets, RL, particularly with DQNs, learns directly from interaction, making it ideal for problems where optimal actions are unknown or difficult to define beforehand. A key limitation remains sample efficiency. DQNs often require millions of interactions to learn effectively, a stark contrast to human learning. Addressing this has led to advancements like curriculum learning and curiosity-driven exploration, where the agent seeks novel experiences to accelerate knowledge acquisition. The true power lies in building adaptable intelligence, systems that don't just execute predefined rules, but autonomously discover superior strategies. DQNs represent a significant leap in forging AI that learns, adapts, and masters complex dynamic environments, transforming how we conceptualize intelligent agents.